Welcome, everybody. It's great to have so many people turning out to learn about hydrology. I know it's something that I don't know a lot about myself, but I know that it underlies sort of everything we're doing here at the NRWA. So I'm looking forward to hearing this presentation with Dave. Welcome to everyone. For those of you who aren't familiar with the Nashua River Watershed Association, we're a nonprofit environmental organization. We do water and land protection, climate resilience, and environmental education programs in 31 communities in our watershed. Watershed is a hydrologic term, and you'll be learning about that, what that means later. We are supported by members and donors, some grants. For those of you who are already members and donors, thank you so much because you make programs like this possible. And if you're not a member or donor, we certainly invite you to learn more about us, and you can check out our website and see if you want to join. The website is nashuariverwatershed.org. Now I would like to welcome Dave. So the NRWA is incredibly lucky to have a very talented board of directors. They come with different skills and expertise, and Dave's is expertise in hydrology. In 2023, he retired from a 34-year career as a hydrologist with the US Geological Survey, and he did his work both here in New England and in Minnesota. And he did a lot of work on stream flow and habitat, groundwater and surface water interaction, wetlands and water quality. He's currently still working with us as a river guide for our river classroom during the spring and fall seasons, and that's a program that takes school children out on the river for a day-long paddle and science exploration. He also was a water monitor volunteer for us for 25 years. He's on the board of directors for our local Trout Unlimited group, the Squanitussit group based out of Pepperell. And he's also on the board of the Neshoba Conservation Trust. And he is a member of the Pepperell Climate Change Committee. He did his bachelor's work at Hobart College, and he studied hydrology at the University of Minnesota. And with that, I pass it off to Dave.
So hi, everyone. Thanks for joining. It's nice to see everybody out here on a February night. I know we've got a lot of snow right now, but it won't be long before the rivers will be open and looking like they are in this photo, the Nistissit here at the beginning. So I'm going to talk tonight about hydrology. It's a pretty broad topic, and we're only going to kind of skim into it a little bit, but we'll dive right in here. I'm going to spend some time talking about the water cycle in the Nashua River Watershed, and then we'll kind of look at the water's journey through the water cycle, spending a little more time in groundwater and surface hydrology, and a little bit on flow alteration before we wrap it up. So the water cycle and hydrology. Hydrology stands for the study of water, and particularly the study of water through the different components of the water cycle. And we've all kind of learned about the water cycle back in elementary school. I mean, we'll be talking about it in more detail here, but it basically describes the continuous circulation of water between the atmosphere and the earth and through the subsurface of the earth. But before we do that, I'd like to kind of take a step back and think about where that water comes from. Most of the water in the water cycle is coming off of the oceans. About 97% of the Earth's water is salt water. There's only 2.5% that's fresh water, and most of that is stored as ice. So with only a small percentage of water is fresh water, how do we have enough water? It's because, again, of this constant replenishing of the water cycle that we have water to use. And I'd also like to point out that though we'll be talking mostly about the water cycle in the Nashua River watershed area, it's really the global water cycle is important to think about because 90% of the evaporated water that gets into the water cycle comes off the oceans. There's a lot of direct sunlight onto the equatorial part of the earth, and there's a lot of ocean. If you look at the size of the Pacific in that in the equatorial region, and a lot of that water evaporates in that part of the earth and circulates up into the higher latitudes where it can move across, say, North America with the westerlies or up with the Gulf Stream. But when it comes to effects of climate change, the oceans absorb a lot of the heat that's come from global warming, so it's kind of speeding up the water cycle, and that'll be the subject of some of our later talks with this series. So first off, I'd like to look a little bit about the setting of the Nashua River Watershed and where we're located. and talk about watersheds in general. So a watershed is a geographic area of land that's drained to a single outlet. So any rain or snow that falls in a watershed exits out a single point. And it's bounded by what's called a surface water divide. And you can think of this as, often think of it as being like a ridge where if the rain falls on the watershed side of the divide, it ends up in the streams or rivers in your watershed. If it falls on the other side of the ridge, it flows into another watershed. The divide isn't always a ridge or a hill. Sometimes it's a low area that could even be a wetland that flows in a couple different directions. The Nashua itself is part of the Merrimack River Basin, which is a large drainage area that drains a good part of New Hampshire. It actually has a drainage area of about 5,000 square miles. So here we are down in Mass in the Nashua Basin. The Nashua River flows to the north and joins the Merrimack up in Nashua, and then the water flows down and exits the Atlantic Ocean down near Newburyport and Plum Island. Watersheds come in all sizes. So the Merrimack watershed is about 5,000 square miles. The Nashua River watershed is 530, but you can come in any size for a watershed. So the Squannacook River watershed, which a lot of us know, is about 70 square miles, and Little James Brook, which sits right across from Groton Hill Music here in Groton, is about 3 square miles. So they come in all sizes. And here's a map of the subbasins of the Nashua. So you might be able to take a second to look at this map if you live in the Nashua watershed and figure out what basin you're in. I live up here in a little tributary that flows up into Pepperell. So my watershed actually isn't on this map. It's kind of in this area here. But there are kind of 4 major subbasins of the Nashua River. The lower part of the basin, or headwaters of the basin, are down here in the South Nashua. That's the Stillwater and Quinnipoxet. The areas around Fitchburg and Leominster all have a number of small little subbasins that drain into the North Nashua River. Then there's a number of little watersheds that kind of drain directly into the main stem of the Nashua. And the next 2 largest in size are the Squannacook and the Nistissit River. If you don't know what watershed you live in, the USGS Stream Stats tool is a great place you can go to and click on a stream near your house and see if you're in that watershed, or it even has a raindrop tool where you can click on your house and see where the water would go from where you live. So the Nashua Basin itself is kind of in a transitional area. We're on the outskirts of the greater Boston metropolitan area. So we have a few areas of urbanization, but we also have a lot of areas of forests and fields and hiking trails and open land that we can get into. It's the reason that a lot of us live in this area. It's also a transition in between ecoregions. So it's between the Northeast Highlands ecoregion and kind of central Mass up into the higher country in New Hampshire and Vermont, and the Northeast coastal zone. A lot of you kind of intuitively know this if you've ever driven in the winter from Fitchburg or Ashby, kind of down across through Groton towards 495. It might be snowing up here in Ashby or Fitchburg, and when you get down toward 495, it'll turn to rain. So there's a little bit of climate difference between eastern and central Mass, and Nashua River Basin falls right on the border of that. It also falls on the border of higher country to the west and lower country to the east. So the headwater streams for the Nashua rise up here in the west side of the basin in higher elevations. And they have a little bit different character than the streams that are in the eastern part of the basin. So if you're walking around a headwater stream, say at the headwaters of the Squannacook up in Townsend, and you're up in the hills there, you might be walking around rhododendrons and hemlock, and as you get down to a stream, the stream will kind of be steep and rocky, and it'll have boulders and cobbles and little riffles and waterfalls. If you were walking around a similar size basin or stream in the eastern side, you might be walking along through a beaver pond and lower gradient stream. So there's some different in character from west to east across the watershed. And that's interesting to note. Now the river flows from south to north. And if you notice, if you look at the watershed drainage map, The river doesn't even flow down the center of the watershed area like it does in a lot of basins. It's off to the east side. And a lot of the tributaries come down from the northwest. So you might wonder why the stream takes that kind of direction in its flows, and it has to do with the underlying geology of the area. The northeast trend of the Nashua River Valley itself follows the trend of the metamorphic bedrock in this area and the geologic faults in this area, which all kind of trend to the northeast. So there's a kind of some areas here that have softer metamorphic rock that were a little more easily eroded than some of the bedrock around it. And there's some large faults that come up through the middle of the Nashua Basin, and that's the general direction of the trend of the main stem. And then up in Pepperell, there's actually a little brook called Gulf Brook that follows right along this northeast trend of this Weaky Peaky Fault. So the underlying bedrock controls that northeast trend of the river, but the tributaries all come from northwest to southeast because they're following the direction that the glaciers moved across Massachusetts. So when the glaciers moved across Massachusetts, they were a mile thick. They carved a lot of land underneath them and generated these valleys, and a lot of the tributaries kind of flow along those valleys from the northwest to southeast. When the glaciers were here, they actually left a lot of sediment on top of the bedrock, so that's called the surficial geology as opposed to the bedrock geology. And for the most part, the surficial deposits are two different types. There's glacial till, which is a mix, if you look at the photo here in the upper right, mix of clay and sand and gravel and cobbles and boulders that are all mixed in together. And a lot of the hills in Massachusetts actually have glacial till as the underlying sediment. The other type of sediment shown kind of in orangish brown here on the map is stratified drift. If you look at this photo here, you can see that is layered in these horizontal layers, which is where the word stratified comes from. And the reason that it looks like that is that the stratified drift was all deposited out into water bodies, and there was a chance for the sand and the gravel to sort out and layer like that. And the reason that happened was when the glacier was retreating. So you imagine a mile thick glacier ice that had retreated back up around the Mass New Hampshire border. And if it was a mile thick, that's a lot of meltwater that would come off that. And so along the margins of that retreating glacier in Massachusetts, there were a number of glacial lakes. There was one over in Sudbury area. There's one here in Nashua. There's one out in the Connecticut River Valley. And so ours was called Glacial Lake Nashua. And it was this enormous glacial lake. If you imagine you've stood on the shores of Wachusett Reservoir and looked at how large that is, imagine if the lake went all the way up to Nashua. So it was a huge body of water, of meltwater, and the glacier was pouring meltwater streams into that, and all the sand and gravel came into this valley. And if you look at where the stratified drift deposits are, they pretty much follow the general shape of that glacial lake. So those are important because a lot of our water supply wells for towns that get drinking water from wells are in the stratified drift in those valleys. Okay, so let's follow the water cycle a little bit on its journey through the land. I'm going to take a little bit of time with kind of each of the main parts of the water cycle, and we'll talk about those in a little more detail as it makes its way through the ground into the streams and downstream. So the water comes onto the earth as precipitation. We all know the different forms that we might see: rain or freezing rain, snow. But we also get some amount of moisture from dew and fog drip that adds to the soil moisture. In some places, this can be pretty significant. The Pacific Northwest gets a lot of moisture from the fog. We get a little bit in this area from dew when it's humid. So when it rains, the first thing that the precipitation hits is, in this area, since it's mostly forested here in the Northeast, is the tree canopies. Now, we all know that, when you get a little rainfall, you can duck under a tree and stand there and be out of the rain for a little bit. But then if the rain starts to fall more and harder, you'll start to get wet. It'll come through the tree, and you can actually go underneath a tree after a rainstorm and have the water dripping off the tree onto you. So the tree canopies play an important role by intercepting a lot of that rain, slowing down the impact to the ground. So the water will hit the leaves and the trees. From there, it can evaporate again back up into the atmosphere, or it might run down the stem and get absorbed by lichens on the tree trunks or moss and bark, or flow all the way down the trunks to the ground. That's called stem flow, or it can drip through the vegetation onto the ground. And that's the important thing that the tree canopies do, is they help prevent the rain from hitting the ground really hard and causing erosion. That reduces the impact of rain onto the surface of the ground. So it's interesting to look at what happens when the water gets to the ground. If you're out in the forest, you've got all these leaves and leaf litter and duff on the soil of the forest floor, and that actually helps water to infiltrate into the ground. A lot of you might have seen surface runoff. If you go out in a hard rain on your lawn, you can see water running through the grass down slope. And that happens a lot because a lot of the lawns around people's houses are compacted soils, and the water will overwhelm the ability of the soil to infiltrate, and the water will run off. But in a forest or other areas, the water will infiltrate slowly into the ground, and it will, first thing it does is replenish the soil root zone moisture. And it takes time for that to happen. Like some of you may garden like I do, and I'll run my sprinklers for an hour and think I've done a good job of watering my garden, turn them off and go pick up a handful of the soil, and I'll have about an inch of the top part that will seem wet. So it takes a while for that moisture to move down into the soil. And if it does, usually it kind of goes straight down, but it might encounter some rocks or clay and move a little more horizontally. Water moves under the force of gravity, so it will flow down slope if it has the opportunity to do that. Any water that percolates deeper can end up becoming groundwater recharge. So the trees will take up a lot of the moisture from the soil and other plants and transpire it as water vapor out of the stromata and the bottom of the leaves up into the atmosphere. And that plays a real critical role in maintaining a local water cycle. The water that the trees transpire will increase the humidity, and that can rise up in the air and condense and become clouds, which can bring in the rising air, can bring in air circulation from other areas, which can lead to more rainfall. So tree canopies and forests are important for a small water cycle in addition to the larger water cycle that comes off of the ocean. So what happens to the water when it hits the ground? It depends on what the material is on the ground and how hard it's raining and what the conditions are in the ground surface. So if we kind of step through these, if water is landing on an area where you've got bedrock near the surface, it's going to run off. If you have coarse sand or gravel in your area, the water can soak in pretty quickly. If you have silt or clay, the water would tend to run off of those pretty quickly if it's a kind of a clay soil. And then peat is kind of a funny one to think about, because if you get in a wetland and you pick up a handful of peat, it seems like it'd be pretty porous. But what happens in wetlands is the water table, the water surface in the wetland tends to be pretty high, and it can fill up pretty quickly, and then the water can run off into the stream pretty soon. So depending on how hard the rain is falling, it can actually overwhelm the capacity of the soil to infiltrate or soak up the water. But there's other things that can lead to that being runoff happening real quickly, and that is if the soil is already wet from a previous rain. Some of the biggest flood events we've had massive. We had one in the 50s where there were two back-to-back hurricanes. So like in 55, a hurricane came through and saturated the state, and then another hurricane came through shortly later, and the water couldn't soak in at all, ran off, and caused a lot of serious flooding. Another thing that can cause runoff is frozen ground. Frozen soil will act kind of like bedrock, and the water can run right off pretty quickly, and that's part of the reason the stream flows come up pretty quick in the winter. Man-made surfaces, of course, contribute a lot to stormwater runoff. So sidewalks and driveways and roads and roofs are impervious, and the water will run off those immediately. And also the area underneath those sidewalks and roads isn't available to have water infiltrate down into the soil. When the water runs off the land, it collects in small runnels or hills and flows downhill. They might accumulate and flow directly into a stream or a wetland or a pond, or they might accumulate enough that they start to form a small headwater stream. So headwater streams are really important. Most of the water in our rivers comes from small headwater streams. And they come in kind of different types. There's ephemeral, intermittent, and perennial headwater streams. Some of it has to do with the size of the drainage area that contributes to it, but an ephemeral stream is one that only flows, during a rainstorm or right after the rainstorm. The water will run off and run downhill, and then a while after the rain event is done, it'll dry up again. An intermittent stream is just that. The flow is intermittent. So it might be that the water table in the spring might be a little bit higher. Soil moisture might be higher, so you might have a little bit of groundwater coming to the stream, and it might run for a while. And then once the leaves open up and the evapotranspiration kicks in, the upper part of that stream might dry up. Or if you live kind of in a hilly area, you might have an area where you have a small stream of water that comes down and hits a real rocky gravel area and then kind of goes underground for a little bit and pops out a little bit downstream. So these intermittent streams don't run continuously. The ones that do are called perennial streams. So a perennial stream is a stream that runs year round. They have a big enough drainage area and mass. That drainage area is about 2 square miles. And they have a little bit of the water table that intersects the channel, so that there's always groundwater coming into the stream. And that's why you have the stream running during periods between rains. Headwater streams are real important, and those are the ones that that we need to protect maybe the most. So let's talk about what happens when the soil gets saturated and the groundwater flows to the stream. Spend a little bit of time talking about groundwater. Groundwater is the area, in the earth where all the spaces between the grains of sand and gravel, or all the cracks in the fractured bedrock, have filled up with water. So if you were to dig a hole down into this, like maybe you did as a child at the edge of a lakeshore, that the level of the water in that hole or in a well is called, the top of that is called the water table. The area above the water table is called the unsaturated zone. Now, there can be a lot of water held in the unsaturated zone and soil moisture, but you can't pump that water out with a well. The water is held pretty tightly to the soil grains by capillary forces. So water moves by the force of gravity. It moves down towards surface water bodies. You know that it's got to be moving underneath you, because if it's raining and the water is soaking in and it wasn't moving away, eventually all of the spaces would fill up right up to the land surface, and that doesn't happen. So the groundwater, once it's infiltrated, moves off towards surface water bodies. Now, it moves pretty slowly. It moves from higher water levels to lower water levels, and the rate that groundwater moves can be measured in only inches or feet per day. So, in a sandy aquifer, 3 feet per day is a common number to come up with for the rate that groundwater will move. So it might take the groundwater days or years to get to an area where it can discharge to a stream if it's a long distance away. If the water has infiltrated enough so it gets deep into the ground, it might take even a century for the water to come up into another water body. There are even places around the country, like out in the Oglala Aquifer, out in the east side of the Rockies, where the aquifer was recharged as the glaciers melted. So the water has been down in the ground for millennia, and it takes a long time for that water to come out. But for the most part, in Massachusetts, we have these shallow, unconfined aquifers of 20, 30 to 100 feet thick. The shape of the top of the water table tends to follow the shape of the land surface. So if you're in a hilly area, the water table is usually higher there than it is in the lower area. So water moves down gradient towards water bodies, and discharges up into the stream or a lake in a spring or a seep. And a lot of you might have seen an area where it does that. One of the things that happens as the water moves through the ground, it tends to be anoxic, doesn't have oxygen. So any iron coatings that it's picked up off the sand grains can move with the water until the water hits an area where it gets oxygenated, when it can precipitate it out, or iron bacteria can precipitate it out and use it for energy. So you see these kind of orange films along the shoreline. Some people get worried that those are pollution, but generally they just indicate that that's an area where groundwater was discharging. Another way you can find these seeps or springs is by the temperature of the water. The groundwater temperature tends, because it's down in the ground, it's away from the sun, it's in the heat from the sun, it tends to have a temperature that's about the same temperature as the average air temperature, which in this area is around 50 degrees. So in the summer, if you're wading in a river fishing without your waders, you can really feel where the water is coming in springs or seeps, because the water is a lot colder than the stream water. And in winter, 50 degrees is warmer than the stream, which might be down around 0 or 5 or 10 degrees. So you can see where groundwater is seeping into streams, because the ice might be melted in that area. Another place that you can see springs and seeps showing up a lot is along a break and slope. When you're coming down a hillside toward a stream and it takes a break and slope at the floodplain as you're near the stream, sometimes your first steps off that hillside are you're going to get your feet wet, because that's an area where springs tend to discharge upward and then move horizontally through the floodplain toward the stream. We've got a number of wells in this area that monitor groundwater levels. There's 4 or 5 of those in the basin. I say 4 or 5 because there's one down right about on the watershed divide in Berlin. It's a bedrock well, about 500 feet deep. But the wells that we have in the basin, there's one up in Townsend, it's in sand and gravel. We've got a pair of wells in Sterling, Mass. One's in Till and one's in sand and gravel. And another one, West Boylston, that's in sand and gravel. So this behave a little bit differently. If you go to the websites for the USGS and look at the water levels in those wells, you can see the little differences between how quickly the water comes up in till versus sand and gravel. And the groundwater levels, when you look at a hydrograph for a well, will look quite different than the hydrograph for a stream for the same period. So here in the lower left, I've got a hydrograph for the Squannacook River near West Groton. So this is for the period from last October to this October. And then here on the right, I've got a hydrograph for the well up in Townsend for that same time period from October to October. So one of the things you can note right off is that the stream has all these high flow events. These are rainstorms that have come through, cause the water level to jump up. So you can see when we had the big rain periods, but you can also see a higher spring period where just the flow in the river was higher, kind of in April and May, and that makes sense. But the time here when we're getting snowmelt runoff, that's when the river will be flowing higher. If you look at the groundwater hydrograph, it has that same general shape, but it's all smooth, because it takes time for that water to infiltrate into the soil, and you lose the variation that you get from the rainstorms as it trickles down and infiltrates. One thing that's interesting, if you look at this, again, I pointed out that the high stream flows in the spring in the Squannacook were, March, April, May. If you look over here on the well hydrograph, the high groundwater levels are delayed. It's, May, June, and July. So there's a little bit of a delay in the time period for groundwater to respond compared to stream flow. And then as you get into late summer and you get less rain and more evapotranspiration, the groundwater levels kind of drop into the fall. Some of the driest periods of our streams here are actually kind of in late September, when it's still warm, there's still evapotranspiration going on with the leaves and the groundwater level is dropping. Right, a lot of you might have your drinking water at your house coming from wells and wonder where that comes from. For the most part, it doesn't come from the area, kind of right around your house or in your yard, because any water that would have rained and infiltrated there is going to start moving off with the groundwater toward a stream before it gets a chance to get deep enough to get down to where the well screen for your well is. So the water that gets pumped into your well for your house would have to come from farther up gradient, uphill in most cases, where the recharge would have entered the ground and then had time to work its way down into the aquifer to the depth where your well would intercept it. So the area that recharges the water to your well is probably somewhere a distance from your well. It could be, half a mile away from your house on an up gradient. Now we'll talk a little bit about surface water hydrology. If you look at the profile of a river, the classic profiles for a lot of streams take this shape from high elevations to low elevations. So if you were thinking of this as being, say, the Squanicook coming down into the Nashua, up in the higher elevation areas, you're up in the areas where there's more slope to the streams, so you end up having more rapids and riffles and waterfalls. And if you look at the stream bed in the stream, it's going to be gravel and cobble and maybe some boulders. And the valley of the stream tends to be kind of narrow and V-shaped and maybe run a lot straighter compared to downstream. But then as you get downstream, the valley broadens up as more tributaries join it, and you get a little bit of a valley and room for the stream to start to meander back and forth across the valley. You'll still get some gravel and riffles in some areas, but you probably have a lot more sand in the bed of the stream as it gets down in these gentler slopes. And then you get way downstream. Often the river valley, at least in this area, tend to be a lot wider. Sometimes it's hard to even kind of see the valley of say, the Merrimack River. And the river will meander back and forth between that. It's a lot broader valley. Same thing with the Nashua here that has a pretty broad valley across the Pepperell area. The river biota have adopted to these changes from smaller streams where the tree canopy can totally close over the stream to, as the stream gets larger, the tree canopy kind of opens up because the stream is wider and you get a little bit of sunlight into the stream, and then downstream in the rivers, the river channel is a lot wider. So the biota that live in those areas have adopted to that and into the habitats. So up in the headwater streams, the canopy closes over and shades the stream. In the summer, the area is shaded and water tends to be a little bit cooler. The only food that kind of is available, or the food that's most available for the macroinvertebrates and the fish that live there, are leaves and organic material that drops into the stream. So a lot of the macroinvertebrates that are in these headwater streams are species that can shred the leaves and up and live off of those. And the fish that live in those streams tend to be those that are adapted to colder water conditions, smaller streams like brook trout and black-nosed dace. As you get into a larger stream system, the canopy opens up and you get a little bit of sunlight into the stream and you can get some algae growing. And this is why if you're wading across the river, the rocks are slippery. It has this biofilm of algae that grows on the rocks and grows on the plants and grows on the woody debris in the stream. And the macroinvertebrates that live in those reaches are those that can kind of graze along on that biofilm and use that as their energy source. The water tends to be a little bit warmer, so the fish out there are a little more tolerant of warm water. And then if you get downstream into a bigger portion of the river, the channel widens, the vegetation along the banks has a little bit less effect. And the food for the organisms that live there tend to be phytoplankton that might grow in the still water, or aquatic vegetation that grows in the water, and the organic matter that's on the bottom of the river. So the American vertebrates that live in those larger river systems tend to be ones that can collect that organic matter that's floating through the water. And the fish that live in those areas have to be more tolerant of low oxygen water. So we've talked a little bit about groundwater and surface water. one of the things I'd like to have you think about is that it's most appropriate to think about rivers not just as conduits that transport water from, uphill to downhill, but as a river corridor. You can have water coming in through surface water to a stream, and you can have water coming in through groundwater to a stream. But there's actually a lot of exchange of water from the river into the areas nearby to the river, and those are called hydrologic exchange flows, where the water can move out into the banks or into the wetlands or down into the stream bed of the river. I'm going to talk about that in a little more detail. But those hydrologic exchange flows are important because the water will have the chemistry of river water, but then it goes off and has some contact time with the wet vegetation and wetlands and groundwater, and it can change the chemistry of the water a little bit and the temperature of the water. So let's look at these different components: the active channel, the floodplain, and the hyperrheic zone. The active channel is the part of the river that we think about the most. I think when you first start thinking about a river, that's where the flow is moving through. And the major controls of the shape of the channel are the amount of water that's flowing through it, the bed material, the size of the bed material, the vegetation along the banks, and how confined the valley is. Here in the east, we don't have a lot of sediment that moves with the rivers with every rainstorm like you do out in the Midwest, where there's a lot of agriculture and the sediment and soils can wash into the streams out there after even what we would think of as a moderate rainfall. The streams can turn brown pretty quickly. Here in the Northeast, we've got a lot of vegetation along the banks of the streams, and that kind of ties up the sediment and keeps it from eroding as quickly. So here's a way that the stream can form. Its channel shape is called a meander. So on the outside of a meander bend, when the water hits the side of the bank on the outside of the bend, it has a little higher velocity there. It can erode away the bank, and then it can go downstream and erode away the bank again at the next bend, go downstream and erode away the bank. And after it erodes that sediment, where the velocity is faster on the inside of the bend, the velocity is slower and the sediment will drop out right away in what's called a point bar. So you'll have a point bars form on the inside of the bends and erosion on the outside of the bends. So that's the active channel, but that isn't all the active channel. The active channel is actually more than just the single channel that has all the flow. The active channel also includes all these secondary channels and oxbows that occur along a river. So these are the two river reaches where Nashua River Watershed takes school children for the Nashua River Watershed River Classroom. This is the Route 119 and the Pettapog Boat Launch. Nashua River Watershed headquarters is here. And downstream, if you've floated this reach of the Nashua, you know that there are these oxbows that branch off. This is where the river used to flow. And around these oxbows, and then sometime during a flood, it would cut off the narrow neck of those oxbows and leave the channel behind. So you get these secondary channels that are still filled with water, still provide a lot of habitat and increase the biodiversity along the stream. Here in this right-hand photo is the Squannacook River in West Groton. So this also has these meander bends and oxbows along the river there. So the reason we have these in these areas is what's happening is downstream in Pepperell here on the Nashua, there's a dam. And then here's a dam here for Hollingsworth and Voss. So as the water from upstream comes into this reach, when it hits the very upper end of that impoundment, it slows it down. And it has a chance to drop whatever sediment or wood it might be carrying and start to do some meandering. So the river meanders back and across its floodplain. That's called the channel migration zone. And that's part of the active channel. The other part of the river corridor is the floodplain. So the floodplain might not have a secondary channel in it, but it's a very important component to a river corridor. There's a couple different levels of floodplains that you can think about. You have your normal little floodplains that get flooded, maybe every spring or so with the high water that comes through. But then every few years, we might get a hurricane come through, and you might have a very high water level that floods a much farther distance. So the floodplain actually extends out to the farthest extent of those floods. But floodplains are really beneficial. They help to reduce the water levels in floods. They store groundwater. It's a place for the sediment to be deposited. They help improve the water quality, and they provide a lot of wildlife habitat. Okay, the third part of the river corridor is this hyperrheic zone. And this maybe is a little harder to get your head around, but it makes sense if you think about it. Water actually flows from higher water levels to lower water levels. So I've got two plots down here on the figure. This one's a cross-section view, like you're looking sideways at a river. And then this is a map view looking down on the river. So in this case, I've got a diagram showing water flowing over maybe a riffle or a big sandbar where the water is higher upstream and lower downstream. So what happens is the higher water flows from high to low, right? So this higher water level will actually push water down into the stream bed for a short distance through the riffle, and then it'll emerge downstream. So it might take a short path, or it might go deeper into the ground. It won't go down as far as the deep groundwater way down beneath the stream, but it interacts with the stream bed underneath the river. And in this case, we talked about velocity kind of being higher along the outside of the bends of meanders. That can actually force water into the meander itself, when water will travel as a short path of being groundwater again for a while, and then come out on the other side of the meander. So this is actually pretty important, because the time that water is spending down in the stream bed or out in the banks, it's exposed to finer sediments and organic matter and a lot of microbes, and it has a lot more contact time while it's in that environment, and that can modify the chemistry of the water, take out some of the nutrients and some of the organic carbon and metals, and improve the water quality. And then when the water kind of returns back into the stream, it has a slightly different modified chemistry from the river water. It probably have a little bit less oxygen and maybe a more stable temperature. This also provides habitat for macroinvertebrates to live kind of in the materials under the bed and next to the banks. Another way that this can happen is with what's called bank storage. If you think of a river like the Deerfield River, where water gets released from a hydropower release, or any river that has a flood event, water gets a chance to be stored out in the banks because of that higher water level. So I'll step you through these. I've got 4 diagrams here, one with lower water level, and then we have the water level comes up higher and then falls. So when the water level comes up, you think about the banks along the river, those weren't saturated before the river rose, right? So when the river comes up, the water can actually move out into the pore spaces in the bank and out into the banks. And that can actually back up the water table a little bit. Or you might get a higher water level that floods over the floodplain. That's going to saturate all the pore spaces in the floodplain in the ground under the water. And then when the water recedes, that water will come slowly flow back out and back into the river. So that's a similar idea to the hyperrheic zone, maybe on a different scale. That also happens interestingly enough, with beaver dams and beaver ponds. So when a beaver builds a dam, a lot of us think about the water that's in the impoundment itself, but there's actually a lot more water, even more water that's in the impoundment up in the floodplains and behind the beaver pond or next to the beaver pond. There can be 2 or 3 times as much water kind of stored in the wetlands around a beaver pond than in the actual little impoundment itself. There's a lot of ways that beaver dams will affect stream flow. A lot of people view them negatively, but it isn't always the case. But in the late summer, when the stream flows are dropping and beaver build their dams, and the beaver pond is filling up, it actually might slow down or decrease the amount of water flowing downstream. But once the dam is in place, if you've ever walked across a beaver dam, they're pretty leaky features, and the water's kind of leaking out through all the sticks, and they actually can support stream flow downstream during dry periods from all the water that's stored up in the pond. So like in the hyperrheic zone, the water that's stored up in those wetlands it stores water and sediment and nutrients for longer times than reaches without beaver dams. And we'll hear about that in a couple of weeks with Ben's talk. Another thing that besides sediment and water that moves down rivers is wood. It's not something that a lot of us think about because over time, a lot of the rivers across the whole country actually have been cleaned of all the wood in the rivers. And so a lot of people think that it maybe shouldn't be there. But natural streams actually have a lot of wood in the rivers, and it adds a lot of habitat. The wood gets into the rivers by a tree kind of growing out into the space over the river channel to get more sunlight. And then as the tree gets larger, it gets heavier and it leans. And while it's getting heavier and leaning, it might get eroded underneath and the tree will drop in. Or you might have a microburst that drops trees into the river, or maybe in this case, like with the ash borers that we have now, that you have an insect infiltration and the infestation, and the trees die from that and fall in. But once they're in the river, they increase the resistance to flow, and they can cause scour holes underneath the logs. In some cases, they can actually dam up the river channel. So this is the Squannacook River up in Townsend. And there's a channel here, part of the channel where a lot of woody debris had pushed in and piled up. And what happened was it kind of blocked the flow to this reach of the river. And there's another channel that you can't see in the picture, but the river kind of avulsed off in this direction. And the main channel now goes around this reach. So most of the flow goes by this reach of the Squannacook, but the habitat is still here. So it's wonderful habitat for fish or turtles or salamanders to use, and it adds to the biodiversity of the river by leaving the wood in place. All right, so stream flow, we've got a number of stream flow gauges in the Nashua Basin that the USGS and their state cooperators manage. There's actually 7 of those in the Nashua Basin. They're not all in places where you can see them right off the road. For instance, the Nashua River gauge in Pepperell is behind the hydro plant. The Squannacook gauge in West Groton might be the one most people know because it's the area where the cableway crosses and there's a swimming hole there. The one in North Nashua River is kind of on a road you can't access north of Route 2. There's another right next to 190 near Leominster, one down below Wachusett Reservoir, and a couple on the tribs that feed into Wachusett Reservoir. But you can go to these gauges and look at what the stream flows are on the river in real time by going to this website. So what is stream flow? It's actually the amount of water that's flowing down the river per unit time, and it's measured in cubic feet per second, or in other parts of the world, it's in cubic meters. But here in the US, we use cubic feet per second. And it's determined by the amount of water passing through a cross section and the velocity of the water at the time. So to calculate the amount of flow in the river, you've got to know the area that the water is flowing through, and you've got to know the speed that it's going. So discharge is Q, V is velocity, A is the area. So the way that the discharge gets measured is a hydrographer will go to the river, divide it up into 25 or 30 little rectangular cross sections. They don't have to be the same size, and measure the velocity in that section, calculate the depth and width of the section to get an area, and then multiply velocity times area, sum them all up, and that gives you the discharge. The gauging stations themselves don't record discharge directly. They record the water levels. You can't record the discharge directly, but the instruments can record the water level in the stream. So the gauges will have instrumentation that will keep a continuous every 15 minutes record of what the water level is in the stream. And then the hydrographers go to the gauge and measure the stream flow and the water level associated with that. And then they make a plot that relates those. So this is called a stage discharge rating curve, and it relates the water level in the stream to the amount of flow in the stream. And once you have that relation established, you can develop what's called a hydrograph, which is a plot of the stream discharge over time. So down here in the lower part of the figure, we've got 2 plots. The one on the left is the Squannacook River near West Groton, and the one on the right, the Nashua River at East Pepperell. You can see they have a similar shape. These are from January to January. So you can see the high flow kind of in the spring, in April and May on both of these plots. It makes sense, right? Because the Squannacook flows into the Nashua. It's going to have kind of the same shape, right? But what you notice on this right-hand plot are these, all this variation in the water level, and that's because of the hydroelectric plant in Pepperell. It's pumping water and releasing water, and that makes the water level go up and down. So some gauges are around the state reflect kind of a more natural flow pattern, and some of them reflect an altered flow pattern. But once you have streamflow data, there's a ton of things you can do with it that it's used for. It's just used to look at flooding and by the National Weather Service. It's used to decide what size bridges or culverts to install. Or you can look at storm hydrographs. Like here's a storm hydrograph from a tributary stream. Think of one like, the Squanicook or something that is up, in these smaller tributaries, the water level will come up pretty quick and then it'll drop pretty quickly. Further downstream, say at the Nashua gauge in Pepperell, it takes time for this water from the upstream tributaries to get there. So there's a little bit of lag in the peak of the stream in comparison to the timing of it. And it also will be lower. It takes a little bit longer to come up and then a little bit longer to drop down. But a lot of water will pass. If you were to accumulate the area under this for all the tributaries, it'd be the same as the area of volume of flow downstream in a natural river. You can also look at things called flood frequency curves. A lot of us have heard about the 100-year flood. That can be a little bit confusing, but what it relates to is the percent probability of that water occurring in any given year. So for say a 10% probability, that's a 10-year flood. A 10-year flood in this particular river is a flow of about 675 cubic feet per second. There's a chance of that occurring in any given year is 10%. If you start looking at a higher flood that might have only a 1% chance of happening, what happened here? No, the other way. Did it again. Flood event of about 1,000 CFS would be, in this case, would be for a 100-year flood. That would have a 1% chance of happening in any year. So you can have back-to-back years where you have flood events that are high enough that there was only a 1% chance that those would happen, looking at the historic record of the flows. But a 100-year flood doesn't mean that it's only going to happen once every 100 years. It just means that there was a 1% probability of the flood happening in any given year. So also, if you have the discharge, you can look at seasonal patterns in stream flow. This is a pretty interesting plot of some work I did with the USGS. We took a look at the more natural flowing stream gauges around southern New England. And in this plot, the colors correspond. The blue plots correspond to the gauges, that are colored blue on the map, yellow with yellow, red with red, et cetera. But here in the northwest of southern New England, you're up into the Berkshires and southern Vermont and western New Hampshire, where you have these classic New England winters where you have a lot of snowmelt runoff and you have higher spring peaks. So you can see the high spring peak here for these streams. But if you go down into Connecticut, where when you're getting snow in Vermont, they might be getting rain down in Connecticut and Rhode Island, you have a lot lower peak. And it actually comes a little bit earlier because it's raining. It starts raining and snow melt down there earlier in the year in March. So the peak is in kind of March and April instead of just April. And also the winter flows are higher because down in Connecticut, when we're getting snow and it's kind of locked up on the landscape like it is right now in this area is snow, down in Connecticut and Rhode Island, that has already run off to the stream. So the flows will be higher down there. And then down in Southeast Mass, where there's a lot of sand and gravel, the streams have a lot less variability because they're mostly fed by groundwater, which doesn't have that same variation. So those were from natural flow gauges. I need to talk a little bit about the flow alterations in the Nashua Basin. There's actually quite a few of those. They have there's different types of flow alteration. So one of the types of flow alteration is between basins and subbasins. So here on the left is the drainage contributing area that contributes to Wachusett Reservoir. None of that, or very little of that water makes it down the Nashua. It flows off the Quinnipoxet and off the Stillwater into Wachusett Reservoir, and then it gets sent down to Boston for drinking water for Boston and the areas around Boston. We're kind of fortunate that Massachusetts has this wonderful river system, because if we didn't, a lot of the water would have to come from the ground around, or small reservoirs around Boston, and there isn't enough supply from the shallow sand and gravel around Boston to supply the water that's needed for the city. But another type of altered flow is a transfer within the Nashua watershed. So there's a number of those. I'm only providing one example here, but in the upper headwaters of the Squanicook, there's about a 2 square mile area that contributes water to the Fitchburg Reservoir that gets shunted out of the basin and down to Fitchburg's water supply. There are also a number of little reservoirs like this that bring water from outside the Nashua Basin and into the Nashua Basin. So there's water that gets moved around out of the basin or between subbasins. There's also water that gets moved around within a little subbasin. So one example of that is the groundwater that gets pumped for water supply in Pepperell comes from a small tributary up near the headwaters of the Nissitissit. And that water gets pumped. It actually dries up a small stream nearby in late fall there. But the water then bypasses the Nissitissit River. It's out in the water pipes and it's in your house for your drinking water. And it doesn't get back into the river until you get way downstream at the Pepperell wastewater facility. So there's this kind of shunting that goes on where there's water that gets taken out of the tributaries and returned at wastewater plants downstream. And there's 7 of those wastewater plants in the Nashua River Basin that's happening throughout the basin. Another type of altered flow is from the impoundments. The impoundments have the effect of raising the water level, slowing down the water. It makes it easier to paddle, maybe, but it also warms the water up, traps sediment, prevents fish passage across the dams. And we've got a number of large reservoirs on the Nashua. There's a couple down in Nashua, Mines Falls. Maybe some of you have paddled. The Pepperell Pond is a bigger one that a lot of us think about. The Ice House Dam in Air, and of course the largest one is the Wachusett Reservoir itself. We've got a few other ones around, actually a lot more smaller impoundments around that I'll talk about in a second. The other type of flow alteration we have with these larger dams is there's a little bit of hydroelectric generation in the Nashua, 2 mills or hydropower plants down in Nashua, the hydropower plant in Pepperell and the Ice House Dam. Those have the effect of, or at least the top 3 have the effect of raising and lowering the water level kind of on a daily basis. They'll generate water in the mornings, and the water level will get released out of the Nashua, and the water level downstream will come up a foot or so, and then so it's fluctuating up and down. The Ice House Dam in Air is more of a run-of-river dam, but those impoundments affect the water quality and the movement of water through the Nashua. But we've also got a lot of other dams around the Nashua Basin. In fact, the density of dams in Massachusetts is the highest in the country. The reason for that is when the colonists settled the area, there was no power grid. The only source of water was from water power. So they built all these little dams. Anywhere there was a riffle in any of the tributaries that they could put a dam on, they did. And they often kind of used those in sequence together, where they would have several dams from a tributary that they would release water from one to feed the mill. And when that water was used, they would shut it off and open up another dam from another small tributary. So Worcester County, Mass has the highest dam density in the US, and this kind of area in central Mass has the highest dam density in Massachusetts. So there's a lot of small dams. Some of them are still in existence. Some of them are not. If you walk around the streams, any good sized riffle that you get to, if there's no dam there, if you look closely on the banks, you might find the remnants of a dam that had washed out. The other thing that can change flow is the land cover. We have a few urban areas in the basin that show up on the land cover maps, Pittsburgh and Leominster and Air and Clinton. And that, of course, is changing quite a bit. There's been a lot of development in the 30, 35 years that I've lived in this area. A lot of the little larger blocks of forest are getting broken up for development. And that actually has an effect on the stream flow in some cases. Impervious cover from roads and sidewalks causes a lot more runoff. So these are 4 plots that show the effect of impervious cover on runoff. If you don't have much impervious cover, you get about half the water that will infiltrate into the ground, and some of it will run off. The rest will evapotranspirate off of trees. But as you start to build houses and sidewalks, you get a little more runoff and a little less infiltration. And if you have a lot of impervious surface, like in an urban area, you get a lot of rapid runoff and very little infiltration. And the effect of that is called the urban stream syndrome, where you get a lot of flashier streams where the water runs right off the roads and directly into the streams. The river water level comes up quickly and erodes the bank, cuts the stream channel down into the bed, washes in nutrients, and affects the biota that live in those rivers. So I don't want to end on that note. I wanted to talk a little bit more about the basin. There's a lot of good things going on in the Nashua Basin related to the land and the rivers, and those are recognized around the state and by state agencies. There are some areas in the Nashua Basin that are denoted for their outstanding environmental values. So there's an outstanding resource water classification for rivers that are used for water supply and that have high water quality. There's this ACECs, areas of critical environmental concern, where there's areas that have real high biodiversity and some rare species. There's only a handful of these around the state. We actually have 3 of these in the Nashua River Basin. There are a number of cold water streams here that are designated cold water fishery resources, where Fish and Wildlife has done electrofishing and found we have intact or brook trout populations. So the streams in the western part of the Nashua Basin have some of the more intact brook trout streams close to Boston, up in the headwaters of the Squanicook or Nissitissit. And there's also on the main stem itself, the National Park Service recognized the value of the rivers by designating them as a wild and scenic river, the Squanicook, the main stem Nashua, and then the Nissitissit River. So there's a lot of recognition of the high quality of the waters in the Nashua River watershed, and there's also quite a bit of land that's been conserved, and this is fantastic. It's part of the reason that a lot of us live here is we have access to the waters and to these lands to hike and walk on and explore. So the state agencies that do GIS work in Mass and New Hampshire have determined that there's about 100,000, 104,000 acres of conserved land within the Nashua River watershed. So that's 30% of the watershed that is not going to be developed. It isn't all kind of conservation land. Some of it might be parkland, but it's not going to be paved over. Then we also have a lot of land along the rivers that has been preserved in the Nashua River Greenway. There's about 200 miles of riverbank riparian areas along the river that have been protected. And in some of our river tributaries, like the Squanicook, 66% of the banks along the Squanicook have been protected. So that's just fantastic. So that's where I'll leave you, and hope everyone gets a chance to go out and explore.
Thank you so much. That was wonderful, and I loved ending on the positive note of looking at all that conserved land, especially now that you've explained how the water interacts with the shorelines, and it's all very important. It's all tied together. Okay, so there were a few questions about wells and how old the water might be in a well, and I like Tony's question. He said, "How old's the water in my well? Did a dinosaur once drink it?"
Yeah, in most cases not. I mean, the most of the wells we have here we don't have deep aquifers here. In some parts of the country, they've got layers of bedrock that go down hundreds of feet that could have fairly old water. There actually are ways of dating the water, looking at tritium, for instance. You can determine the age of the water in a well, but no, it wouldn't have been that old. Usually it's a few years old. Days to weeks to years is more the age of the water.
Right. So at one point we know that the earth was really salt water. Was there ever a point in time where it was all fresh?
Um, no, I don't believe so. I think as you know, there wasn't a lot of vegetation early in Earth's history, and so there was a lot of chance for uh, salt and other other solutes to wash into the ocean. So I think it actually built up as salt water pretty quickly. I don't know a lot about that, but I don't think there was a period where we had oceans that were all fresh water. I think over time, as they filled up with water, it became salty.
We have a question related to your slide that showed the seeps and the orange bacteria. The question is, why is it called iron bacteria?
There's a bacteria that can get energy from converting the dissolved iron in groundwater from Fe2 plus to Fe3 plus. So it's taking advantage of that conversion of iron that's dissolved in the groundwater because the groundwater tends to be anoxic, and so it's called iron bacteria. There's another name for it. I can't remember the Latin name for it, but what it's doing is it's precipitating that iron, and it's basically rust, right? It's converting it from being dissolved in the water to the rust form, which is what you see it where the springs are coming in.
All right. Can microplastics leach into the aquifer?
Oh, absolutely. I mean, microplastics get pretty small. I mean, the larger microplastic particles are big enough that they would be, screened out by water soaking into the ground. But we have, microplastics in our bodies now, and they can be so small that they'll move with the water. They move a lot more in surface water than they do in groundwater, but they'll move with groundwater.
And I know later in the questions, somebody also asked about PFAS contamination, if that can leach into drinking waters and aquifers.
Well, PFAS is a big concern. It's called rubber chemical because it doesn't break down. So and it moves with the water. So it's not something that you really filter out without having these, real expensive filters that some of our towns are having to put in and pay a lot of money and change those filters often. We've got a couple wells up in Pepperell that have one well in Pepperell that we had to turn off because of high PFAS levels. It was actually real close to the Nashua River and maybe induced some infiltration from the river into the well by pumping. We've got another well that has kind of right around the marginal area where they're going to have to start treating that water. But yeah, PFAS moves with the water, and it seems to be not everywhere, but it's some places where it's pretty high concentrations. It was most of the big spots are in areas where they use firefighting foam. So I know down on Air Force Base on Cape Cod, they were looking for hot spots where they, down there, and like they had cases where someone say, "Hey, do you remember that, that plane accident that we had, 30 years ago, and we had to put out with the firefighting foam from the trucks?" And they would drive to that area and sample for the PFAS, and it would still be there in that same exact spot where someone remembered where the accident had happened. So it does bind to the soil a little bit, but a lot of you have probably read about the areas up in Maine where they spread organic material from the wastewater plants out on the farm fields, and it's gotten into the into the ground, into the plants, and they actually into the animals, the deer and turkey. In some of the counties in Maine, they've had to shut off hunting of those because they have high PFAS levels in their bodies. So it's a concern. It doesn't come from the wastewater plants. It all flows to the wastewater plants. They're not the source of it. It comes off of polyfluorinated compounds like in Teflon is the one that people talk about, or Gore-Tex, or the Scotch spray that got put on your furniture and your couches or your cars. They had PFAS, and it was used in ski wax. So it was used in, it's a compound that was used in a lot of places. So it's kind of all over the landscape, different concentrations.
All right, we have a question about whether a shallow dug well is likely to have better water quality than a deep drilled well.
Usually you're better off with a deeper well because the water's had more time to kind of filter through the ground. It might depend on what materials that you're well is drilled into, there is kind of a band of rock across. It actually crosses from New Hampshire down into the Nashua area that has high levels of radon and arsenic. That there's some reports the USGS put out on that. It depends on what materials the well is developed in, but a real shallow well, there's a greater chance that the pesticides or fertilizers that get put on lawns are going to infiltrate down and get into your drinking water before they get a chance to get bound up by the soil much. So usually you're better off with a deeper well than a shallow well.
Somebody asks, are the waterways in the Nashua River watershed healthy in terms of plants and wildlife?
Some of them are very healthy. So the Mass DEP has a program where they go around and sample macroinvertebrates to look at that. They have to put out, as part of the Clean Water Act, they have to sample streams around the state. I didn't get into water quality much because we were talking mostly about flow. But there are some very high quality streams in the Nashua Basin, mostly up in the tributaries, where you haven't got wastewater flow coming into those, or a lot of urban runoff.
All right. Let's see. Can you comment on the difference between the capture zone for a private well versus a municipal well?
Sure, it's a lot smaller. So you think about the volume of water that gets pumped, for a municipal well. They're pumping. They don't even get permitted till they're over 100,000 gallons a day, and we don't pump that out of your individual well. So the contributing area to the public water supply well will be a lot larger than a private well, which would be probably a smaller area.
All right. Sarah comments that PFAS is also in home wastewater and can enter the groundwater via septic systems and leach fields. And I see Lori Nearing has shared some information about some legislation that may be before our Massachusetts legislature, and we'll try and share some of this in a follow-up email with folks. Let's see. Understand that activated carbon filters work and will take out PFAS and radon. Is that accurate?
Yes, I think it is. I know that the activated carbon filters are in the filters. The public water supplies like in Pepperell are having to build a new plant and put in large filters to take out the PFAS. So I know it can be removed. I'm not sure about the little home units. I've spent a lot of time actually sampling for PFAS. We had some projects with the USGS where we looked at, PFAS in rivers and PFAS coming out of wastewater facilities. And we actually looked at sewage treatment plants that drain urban areas versus just residential areas to compare the PFAS water levels in those. But I think it can be removed.
I was just going to see, Lori Nearing, did you want to unmute? I know you've done a lot of work with the PFAS situation in air, and I see you've posted that these filters remove longer chains, but maybe not the shorter chains.
Okay.
Yes, that's correct. I am doing a lot of work, and I'm working to pass those two bills as well. Carbon filters work partially with the longer or more traditional forms of PFAS that have 8 carbons. Now we have new PFAS that are much shorter, and they need other solutions. But there are filters that we can purchase for at-home use and private water wells and our towns and villages that are effective. But it's removes the PFAS, doesn't break them down. As David already said, it's a really strong bond. So the real solution is to stop using so much of it. And like David was saying, it is everywhere. Everywhere we look, we find it across the world.
Thank you, Lori.
Yeah, you're welcome.
Utkir has a question. What hydrological signals would tell us the watershed is becoming less resilient?
Well, the flashiness in the streams from urbanization is one. If you get a lot of runoff off of impervious surface, the water levels will come up and then drop back down pretty quickly. Chloride levels can build up from road salt application to streams. I know in Acton they've been doing some monitoring of road salt, near Conant Brook over time, and they've seen that, the road salt can get into the roadsides and into the groundwater, and sodium chloride levels, in the groundwater will increase over time. So that's one way to look at that as kind of an indicator of what else might be in that water as well. Other hydrologic signals are maybe you get less infiltration because of urbanization. So you get lower stream flows in the summer than you would have had naturally. Or you don't get, because the rivers are impounded somewhat by dams, you don't get the high flows that you need to kind of flush organic material off the stream bed so that fish and macroinvertebrates can use that habitat. So one of the things you can do is compare the hydrographs of streams that are in natural areas, called a natural flow hydrograph, and see how those differ from hydrographs that show the flow in the river. So I did show those two hydrographs showing the effects of the hydropower fluctuations from the hydro plants. Certainly not as bad here in the Nashua as out in the Deerfield, where there's 10 plants that are fluctuating the water on a daily basis. It depends on the type of flow alteration. So the other thing that might happen is you might just have less water in the stream. If it's pumped and diverted through water supply systems, you might have a lot lower flows in the summer. When they first started out my career, I spent a lot of time working over in the Ipswich River, which was getting totally depleted by groundwater withdrawals. So they didn't have any flow, and it dried up in the summer. Now they've hooked up to NRWA water, so they've got water back in the river there. There's a lot of hydrologic signals that can show that.
And this may be a question that will be addressed more in our second program, but Tony asked, with climate change and more extreme rain and drought events, how will the aquifers be affected?
It's a good question. I think we still have quite a bit of rain, and it depends on whether we get longer periods without rain. One of the things that I've been thinking is happening, although I haven't been reading a lot of the literature, but I think we're getting more drier periods kind of into the late summer. At least in my garden, I know that that we'll start out in a year and it'll be a wet year, and I'll have almost more water than I need in the spring, and then we'll go weeks and weeks and weeks in late summer without having any rain. So the groundwater level will be dropping during that period. We might have more extremes between the high flow periods and low flow periods related to groundwater discharge. I think though in the Northeast, there's some areas because of climate change, we're actually getting more precipitation. So I think that's something that Sarah can talk about in her talk.
I see Sarah smiling. She's making notes. Would a dam 4 miles upstream of town wells support the recharge of the aquifer, or would it have any effect at all?
I guess I don't know where you're talking about. A lot of dams are built on constrictions where there was already a riffle, or in some cases there might have been a bedrock area where the dam was built on, where maybe a lot of the groundwater had to come up into the river before that point anyway. But if there's a lot of leakage around a dam, it's usually not a good place to put a dam. I don't know, probably a lot of people aren't familiar with it, but there's an area down in Rhode Island called the Big River Management Area where they had purchased, 13 square miles of land by eminent domain. They were going to build a reservoir like the Quabbin Reservoir in Rhode Island, in central Rhode Island. And it turns out that it was too sandy. And if they had built a dam, all the water would have kind of seeped down into the sand and gone around the dam. So that can happen. But I don't know what situation you're talking about, but dams do kind of force water into raise the water levels around them in the ground. So it depends on where the wells were located relative to the impoundment.
I have a question which relates to droughts. You see the watering bans and things that happen, and I've had people say, I don't have to worry about that because I'm on a well. what I'm hearing tonight is like all the water is connected.
Absolutely, it's all connected.
So
So
is that true?
individually, that well might not make much of a difference, but cumulatively, yeah, the water all comes from the landscape, and the cumulative effects of water withdrawals, it can be pretty large. I mean, we in this part of the country, we don't think about the effects of lawn watering as much as they do in other parts. If you get out like into the Pacific Northwest, a lot of people have xeriscaped their landscape. So they don't have to mow the lawns, they don't have to put fertilizer on it, they don't have to put pesticides on it. They've got natural vegetation growing in their yards, and that's how I treat my yard. Actually, I have a lot of shade, so I have a lot of moss, but I only mow it a couple times a year. And then when it gets tall, I get more toads and snakes, and I like to see that. So
It's my yard.
yeah, better
I see
not.
Brewster has his hand up. If you want to unmute Brewster, go ahead.
Yeah, just to add to the question that's just had here, I believe I heard, and someone will have to check this, that there may be legislation to say that when there is a water ban, it's a water ban for everyone. So, and it gets to your point and what Dave was saying. Yeah, it's a shared resource. Just because a big water producer with a big well is irrigating a lot of stuff, then perhaps they need to dial it back. But there may be an agricultural exemption for it. But I seem to recall that's in the legislature somewhere.
Interesting. Thank you.
The way I like to look at it, Win, is there are times in late fall where you can go to some of the streams, and the flow on the river is not much more than what you'd get out of a couple of hoses. So why put that water on your lawn when you can have it in the river providing habitat? So
Mm. Mm. Tony says, I own a lot of farmland with soils being filtered for public well use. Shouldn't I be paid for my ecological services?
well, we're all pro agriculture. We do have to eat. And by keeping that land as ag, it's not being developed for urban land uses.
Yeah. James from Pepperell Climate Change Committee says, hooray for natural yards. Yards should look more like fields and less like AstroTurf. I think you were saying to me, Dave, that what we don't realize with a lot of lawns is they're actually very packed and they don't infiltrate water as well as more natural surfaces.
When you start looking at impervious surfaces, urban lawns are almost considered an impervious surface in a lot of places because they'll bring the equipment in, they'll strip the topsoil off, they'll hydroseed the lawn. There isn't much loam there to help the water infiltrate, so it tends to run off quicker. That's why there's a big push now to build these stormwater retention basins everywhere and try to infiltrate water. Anything you can do to slow down the water runoff is a good thing. So if you have a stream running by your house, let a buffer of native vegetation go up around it to slow that water runoff before it gets to the stream. That's a very positive thing to do.
So I think that's all for the evening. Thank you so much for everybody coming. We will be doing a follow-up email to everybody once we get the recording cleaned up, and we'll share some resources. Dave has a great list of where he got his slides, as well as some reading that's split out by easy reading to more technical. So thank you for coming.
Good to see you.